All right, so I'm gonna start chapter 8 again. So the last time we talked about certain reactions, but at this time we're gonna talk about the oxidation. Alkene. There's the reaction we call epoxidation. This is simply, we try to make some cyclic ether from the alkene. So this is what we call epoxide. So the process that we're making epoxide compound, the cyclic ether group on the compounds, we call epoxidation. This is also one of the good way to oxidize the compound. Obviously, having this oxygen attached in cyclic form is a pretty good oxidation way. So this is I'll show you one good example. You can try here. So this, okay, over here. And then we're gonna treat with the peroxy acid here. So a good example will be this one, actually. I'll show you the structure. So it looks like this. Okay. And then what they're gonna do is they're gonna grab this one over here. This goes to here. This is what's happening. So this is the kind of how the pair of electron goes there, pair of electrons goes there. But this hydrogen will be picked up by the oxygen in the carbonic group here. So this will be gone, and there will be double one here. Okay. So if that happens, so double one is gone. This. So we can make this compounds here. Did you see how they move so once again, you don't have to worry about the mechanism, but the thing here is if you have a epoxy acid, some type of epoxy acid compounds coming in, they're able to make some epoxide here, so you can do epoxidation. Does it make sense? Okay. So if that is the case, maybe I'll give you maybe one problem here. Maybe can you try this one real quick? Okay, so there. Oh, I'm sorry. That's this way. Okay, so you get this one, right? So once again, so they try to type here, there. This one will be picked up by this one. So they actually, it's technically this one, but and then this one goes there. So there will be double bond here, the single with the hydrogen, and that's this one. And then they're going to have this one is gone. We're only taking oxygen on the cyclic form. That's this. So the mechanism wise is quite complicated, but if you know that just the product from this epoxidation, that's just fine. All right, so there's another way. You can do this here. So if you can try to do this one, okay. So you have this one, and do you remember this one? Halohydrine formation. So what you can do is try to make okay, something like this. Okay, then you can treat it with some base over there and the water. Okay. And then you can try to, what they can do is this will be a lot of hydroxide anion over here, and they will try to catch this one. So then this will be this form. So they're going to have this pair of electron will goes on this oxygen. So then they can use it to attack this carbon here again. And then this chlorine group will leave. So this one goes to the chlorine. So this one will leave, and they also form epoxide over here, because once they leave, they kind of push down to the back, so they come on this same epoxide. So if you have halohydrine formation, and also you can do with some major conditions, you can also make the epoxide. Does it make sense? Okay. All right. So here's the thing. So whenever you have some epoxide here, you can treat it with some acidic conditions. And then this will try to pick up the excess amount of the protons. So they can actually grab this one over there. So if they do that, they make this. And then they try to detach one of the bond here. This cyclic ether group. They try to because this is a positively charged, so it become quite unstable. So they want to be neutral here. Okay, so to do that, there's another push from the water coming into the backside. This is in a wedge form, so they're on like this side. So this another water groups here will come to the back on the back of this chalkboard to attach to the here. Okay? So then this one goes to there. Okay? So this will be gone. Okay? Then you can have hydrogen group over here, but this water come onto the back. Okay, like this. So another water will grab this one, goes there. Then this will become this one. This. Okay. So eventually, you're gonna have the hydrogen group attached on the opposite side. So we call this a trans diol. So the trans means it's on the opposite side. Diol means there are two alcohol hydrogen group. You don't have to know for now, but this is the how you make the trans diol. Meaning, once you form the epoxide compound, if you treat with some acidic conditions, that will form some diol compounds, but it will be on trans if it went through the epoxidation. Because of this part, this is already occupying the one side. This one has to come into the other side. I don't know if you remember this one. If you have a double bond in carbon, when you treat it with the halogens, they form the bromonium ion, right? Okay. So another bromine should come on the other side too. So it's pretty much the same. Because of the epoxide, that has to come, the other water group has to come on the other side. So it shows the trans diol. Yeah. So I'll give you okay, so maybe can you try this one? This one, okay. Can treat it with the either epoxy acid or halohydric formation. Either way, you can say epoxidation. And then treat it with these acidic conditions. So you can try this one maybe 1 or 2 minutes, but we'll do this together. So one thing you can do is there's an implied hydrogen here. Okay, 1 or 2 minutes. It takes some time because there are several steps you need to do, but we'll do this together. So the epoxidation, it could be anything. It could be used this one. Okay, then I form a vein here, or you can do what? It would be the same, right? The epoxidation will be the same. So either way, you can do this one and treat with acidic condition. Okay, 1 or 2 minutes. Okay, yeah, it takes some time, but try to maybe do it step by step. Okay, so if you do the epoxidation, you're going to have this one, right? Okay, and then you can treat it again. This. Does it make sense? Kind of. So okay, so the but you know this one, right? Why you form the epoxide here? No.
Kinda.
Oh, kind of. Okay.
I'm
So
all
let's work on
confused.
this one. Yeah, it's okay. So the okay. This is the part. Maybe I need to explain more. So it doesn't matter either you have a epoxy acid or some other hydrochloric, but I'll just do this one. So what happens here? This will grab this one, okay, and this goes to there, okay, and then this one will grab this one. So this is gone, and this is picked up by this. And now this goes to there, so this will be double bond. Okay, so they become this. But now you have this cyclic formation here, right? And double bond is gone. So they push on the back like this. And then this one comes in. Then you have a lot of protons, right, from here, and this one will grab protons because there are so many of them. So they form this, and then this is unstable, obviously. So this is the kind of a cyclic ether. They try to make it here, but this is pushed by the water. Okay. So this is why this is actually coming onto the back. This is on the front. So this makes neutral, so it becomes this one. And now it came into the back, which is this one. But this is grabbed by oxygen and another water. So this will be gone. This. Kind of makes sense, right? Okay. It's a long process, but technically speaking, only thing you really need to know is when you do the epoxidation, and if you do the hydroxylation here from the acidic condition, they're coming out to the opposite side. That's all you need to do. That's it. Okay. Maybe. Can you try this one real quick and we'll move on? This one, okay. So once again, you can do, at this time you can do this one. It doesn't matter. Okay. But, and then you can do, yeah. Okay. Okay, maybe 1 or 2 minutes again. Check like this one. Okay, about 1 minute. Bless you. Okay, so it's pretty much the same. So if you do this one, you're gonna have halohydrin formation. And then you're going to have a lot of the hydroxide anion from the base. This will pick up the hydrogen here. So the paired electron goes to there. So then this will become water. And this will become negatively charged because donated by paired electron here. And that goes to here to move it. Okay? So this will leave, getting this paired electron as well. So become a negative charge. And now it's pushed. Hydrogen is pushed on the back because they are taking on this carbon. So they become hydroxide. Okay. And then the rest of them are just the same. With this one comes in, so they will make this one water on the back. So will be because the hydrogen will push on the front again. But technically, what happens is this transfer. Make sense? All right. So let's do another one from another type of DSM. So what you can do is if you have a alkene, looks like this. You can also have another way to make some diol compounds, but in a different way. We're using ozumium tetroxide and pyridine solution over there. They and then they're coming on to this. So once again, you don't have to know the mechanism, but eventually they form this one. Okay. And then what it happens to here is you're gonna treat it with the sodium bisulfite, okay, with water. So at this point, the sodium bisulfite is actually going to detach this one, okay? And then the water comes in to make the hydroxy groups on those two sides here. But the thing is, if you look at this osmonium tetroxide coming on the same side, because it's the same compound, right? So slightly opposite side that we did before is they're actually coming on these two hydroxy group on the same side. Because of the osmonium tetroxide came on the same side, so those two are on the same side, right? And then this one will detach this one, and then water comes in to fill up the two hydroxy group. But because of that, they're actually coming on the same side. Okay? So this is cis style because the hydroxy groups that makes this compound alcohol on the same side, so we call this cis diol. Okay, so let me give you one example you can try, and we'll do this together. So maybe I can give you this one. Okay, this one. Okay. So only difference here is diagonal oxidation by adding two hydroxy groups, making diol compounds from the alkene, but it's going to be not at the same position, unlike the one we did a few minutes ago. Okay. Yeah, 1 and 2 minutes, we'll do this together. Okay, 1 minute, and we'll do this together. Okay, so you can try to draw the. So the trick here again is you can try to remove the double bond over here, and then put the hydroxy group on these two carbons where you had a double bond on the same side. So I'm gonna add the hydroxy group on the same side. And this one. So obviously you can see it there. So the point here is just the remove your double bond where you had it in the compound, and those two carbons you put the hydroxy group OH, but at this time we're going to put it on the same side. That's the only difference. Can I move on? Okay. All right. So the another one that we're going to do is what we call ozonolysis. We're gonna use the O3 to break the alkene compounds with the two carbonyl groups. So you're gonna have electrical discharge to make O3 ozone molecules over there. And once you have it, what you can do with this one is here. You have a double bond in some air over here. Okay, and make sure you're in the horizontal way. So if you have this double bond over here, the O3 is just looks like this. Looks like this. So what happens to this one is the pair of electron over here will go to this one over here, okay. And then this one goes to there, and there the pair of electron goes to this one. So if this one happens, by the way, you don't have to know the mechanism again, but if it does happen, it forms something like this one. We call this the molybdenite. Okay, molybdenite. And then what it does is now you can actually put it onto. This is a kind of long step, so you can listen to it carefully, but please focus on the final product. So this goes to there, okay. And then this goes to there, and then have electron on here will go to there. Okay. So if that happens, what happens to this one is this is broken, right? This is broken, and this become negative charge because we got the pair of electron here. This will form a pair of, one of the long pair on this oxygen will make a double bond over here. Okay? So this will become positive charge, this is actually donating. And this one will become double bond over here. Okay? And then what happens here is obviously this is what? Negative charge, so you can attack the carbon here, and pair of electron actually goes to there. Okay, so if that happens, they finally there's okay. So if that happens, finally they form ozonide. It looks like this. Okay, so ozonide. And then when you have this one, you're gonna treat that one with the some zinc catalyst with the acetic acid with water in water. And then what it happens to here is the weak acid here with the protons will grab this one, and then it goes to there, it goes to there. Okay, and then finally you're going to have breakage on here with the two carbonyl groups. Yeah. Does it make sense? Kind of. So the ozonolysis is simply you try to break the double bond where you had the double bond in the carbons, and then you're just adding oxygen there for that each carbon with the double bond. So they form some carbonyl groups over here. So if you have a so if you have, let me see, okay. This one, okay, this alkene compound. Maybe you can try it with the O3, okay. And then also zinc, citric acid, water over here. Only thing you really have to do here to get the final product here is you're just trying to break in this one half, okay? So then this will become like this, right? Okay. We break in half and just put oxygen. That's it. That is your product from the original reactants. So I think the product-wise, it's actually quite simple because you only have to break it and put the oxygen there. There will be a product from ozonolysis. So we call this ozonolysis because it literally breaks the double bond with the O3. So this is breaking, this is the ozonolysis. All right, so maybe you can try one more. This one, okay. Try this one.
Perfect.
That's great. All right, so the next part. Okay, actually, I'm gonna just stop here today. I think